Hi everyone, thanks for joining this session. My name is Tianwa, and today we will present you with our research on building data curation processes with crowd intelligence, which is accomplished by Lei, Gianluca, Marta, Shazia, and me altogether. In this presentation, I will present our research from the following aspects and illustrate our findings from various data curator behaviors and results on learning from the crowd. Based on the background research, we can see that nowadays, data scientists can spend up to 80% of their time engaged in data curation activities, and those cost-intensive and often non-value-adding processes are considered a drain on analytics functions within organizations, and result in data science project cost and time overruns. We can see a primary reason behind the need for data curation is that the large proportion of externally acquired datasets have different quality levels. These external datasets areas are often created for different purposes, and even the internal data needs to be repurposed to meet the specific needs of a data science project. In either case, data curation may include selection, classification, transformation, filtering, imputation, integration, or validation. Therefore, it requires to complete multiple steps before the actual analytics of the data can be performed. Current data curation approaches can be categorized into three types: ad hoc, or we say manual approaches, automatic approaches, and crowdsourced approaches. Even though the recent advances in automated approaches based on AI and machine learning techniques have helped in tackling certain types of data curation tasks, but the bulk of the data curation activities still cannot be feasibly and efficiently addressed by the machine-based algorithm without human intervention. In practice, we can see that manual approaches are still the predominant choice for data scientists. However, such data curation activities can suffer from scalability, lack of repeatability, and verifiability of outcomes. In order to improve the scalability of data curation, recent studies have focused on outsourcing specific data curation tasks to a crowd of data workers online. However, crowdsourced approaches work well for specific micro-tasks, but due to the involved and the contextual nature of data curation activities, and also the inherent complexity of the processes composed by a number of smaller tasks, crowdsourced approaches currently still lack the ability to construct overall data curation processes. Therefore, in our study, we wish to develop a deep understanding of how data workers engage with data curation tasks, especially related to data quality detection, and to investigate how to build a robust and effective data curation process by learning from the wisdom of the crowd. As we can see here, in order to capture the interactive behavior by participants, we design a user interface based on Jupyter Notebook. We use Chrome browser extensions to inject the left and right panel on the top of the notebook, and to log behavior actions by JavaScript. Participants are only allowed to use this given browser in the whole experiment. The UI of our data curation platform has three main panels: Data Ops on the left, the notebook on the middle, and the data on the right. On the Data Ops panel, we provide 21 data ops with a description of its functionality, an explanation of how to use it, such as how to change different parameters. And this set of data ops is sufficient to complete all tasks in our experiment, which are ranging from importing essential libraries to complex Boolean operations involving regular expressions. We also provide a copy button for each data ops to facilitate the copy action. On the middle panel, we provide a standard Jupyter Notebook for participants to perform any operations, either copy, from data ops were written in Python from scratch. We disable the cut button in the built-in tool panel in the notebook to get a full representation of their actions in completing the given task. On the right panel, participants can browse the data they work with and add or remove tag labels indicating data quality issues, either through the toolkit provided in the top right area of the UI or by clicking the tag labels shown in each cell in the data view. The datasets that participants are asked to work with containing 13,000 records, which ensure writing code to perform tasks, and 4 columns including ID, name, contact number, and join date. We prepare the datasets with parallel data generation framework. And the 5 types of data quality issues injected in the dataset are relating to missing, non-unique, duplicate, imprecise, and inconsistent values. This table shows the definitions for these data issues types and the number of instances injected in the data per type. While participants are interacting with the experiment UI, we collect their behavior, which include mouse clicks, copy-paste action, and changes between browser tabs. All behaviors are logged with a timestamp. In our study, all participants were undergraduate and master students in data science disciplines. In total, 39 students participated, and they work on a voluntary basis without a time limit. In order to evaluate their performance of the data curation tasks, we use precision, recall, and F1 score as the evaluation metric. For each tag in our ground truth, if the tag also exists in the created annotations given by our participant, we will consider it as a true positive. Otherwise, this tag is regarded as a false negative. If the tag created by the data workers does not exist in the ground truth, we then consider this tag as a false positive. Therefore, precision, recall, and F1 score can be counted by their definition. Based on the collected data in the log, analysis of recorded videos, and the final code written by best performing participants, we observe their behaviors from the perspective of their strategy in tagging different data quality issues, how they interact with the 3 panels, and how they code, search keywords in external page, and debug when they encounter error messages. As we can see on this figure, there are 13 participants who attempt all tasks. Among them, participants 6, 14, 2, and 58 and 8 are the best performers who achieve the overall top 5 scores. We also notice that the top 5 performers are not all ranked in the first place for all types of data quality issues. And there are 26 participants only attempt several parts of the task. Among the 5 data quality issues, missing and duplicate data are the top data quality issues for which most of the participants achieve a perfect score. However, non-unique is the second best, and inconsistent and imprecise are the third and fourth best. In addition, we can also observe the various behaviors in their coding, such as participant 14 wrote the least code and spent more time on external pages compared to other top 5 performers. And this participant also made effective use of a for loop and regular expressions to reduce the code length. There also exist unique behaviors, such as for participant 58. This participant focused on finding all error types for each attribute, in contrast to the rest of the participants who find one type of error in all of the data before moving to the next error type. In common, most participants copy code from previous tasks to build their next task, and they will view the dataset panel before they approach the task, and during coding and after tagging the data. These behaviors indicating that the dataset view and browsing can provide an intuitive way for data workers to reason about the data quality issues. As the second part of our results, we outline how the collective intelligence of data workers can be harnessed, which aims to improve the efficacy and efficiency of data curation processes. In order to generate the Golden Notebook, we analyze the Python code produced by the top 5 performers for each type of data quality issues. And we start with the code given by those who achieve the highest F1 score for each task. If the participant does not solve the problems for a particular column where the error exists, we will examine the code given by the next best performer. Here is a link for our Golden Notebook. By manually running the Golden Notebook on the same dataset as we use in the experiments, we evaluate the results from the 3 perspectives: effectiveness, robustness, and refinement. In terms of effectiveness, we investigate whether the results given by our Golden Notebook are better than those given by the best performer. As for robustness, we stimulate several scenarios to test if the performance of the Golden Notebook drops when the types of errors become more complex. And as for refinement, we compute the improvement of their performance of the assembled code generated from the algorithm in step-by-step manner. In the following part, I will present the construction of the Golden Notebook as well as the result of the evaluation. Here you can see that for duplicate and missing data qualities, we notice that the participants have already reached the upper bound of F1 score, and all errors of these 2 types were labeled correctly. Therefore, to generate the Golden Notebook, the code given by any of these top performers for these tasks is sufficient. By contrast, the highest F1 scores for inconsistent and imprecise and non-unique did not reach the upper bound of F1 score, so a better solution for these 3 types of errors may be generated. For instance, this table shows as an example of the code given by participant 2 and participant 58, who ranked 2nd and 3rd best in solving the data quality issues of imprecision. Since there is no conflict between these codes, we can assemble them in the Golden Notebook to achieve better performance. In terms of robustness, for instance, we notice that the code provided by participant 2 and participant 14 all works well for identifying imprecise errors in the column join date. We observe that participant 2 used pandas to datetime, while participant 14 used a regular expression with a specific pattern to perform the task. To understand the robustness of the code provided by the 2 participants, we run simulations of their code on an artificial dataset, where we randomly change the instances from the format of join date. And in the simulation of our Golden Notebook, we notice that due to the change of the format representation, regular expression written by participant 14 can no longer match the format, and it shows that writing code in negative logic has more tolerance or flexibility in matching different errors. Among all top performers, we observe that some participants have achieved high precision but low recall, while some of them achieve high recall but low precision. Given the definition of precision and recall, we consider that the performance by means of F1 score can be refined by assembling the code from those with high recall and high precision step by step. In details, we use the code from the participants who achieve the highest recall to select a subset of the candidates to be labeled, and remove the data points where the errors do not exist, while keeping the maximum coverage of the data quality issues for identifications. Then, we apply the code from the one with the highest precision among the top performers to this dataset, which guarantees that we only select from the subset of the instances where the errors are most likely in existence. For instance, we can refine the performance by code snippets given by participant 6, who achieves the highest recall, and participant 46, who achieves the highest precision on the identification of non-unique errors. This table shows that after the refinement, the individual precision is better than, or at least we can say same as the best score for this type of error. In this work, using data science students as a proxy, we study how data workers complete data curation tasks. We have identified different possible data curation strategies and applied a systematic approach to select atomic actions from individual data workers and combine them to create aggregated data curation processes in the Golden Notebook. Our results show that the approaches taken by data workers participating in our study were often diverse and complementary in that they were able to identify different data quality issues with different level of effectiveness and robustness. This bears implications for automatically creating aggregated data curation process through crowd intelligence. However, our work is limited as it was based on lab experiment, and we only focus on detecting data quality issues. And in general, data workers perform a range of data curation tasks. This work is a first step towards a systematic approach to build effective, robust, and repeatable data curation process by learning from a crowd of data workers. In future, we would conduct experiments with real crowd workers to fully test the efficiency of our proposed approach. Such as in our follow-up study, we further provide insights into patterns of interactions with various systems and information to perform data curation tasks. Here is the complete references we mentioned in this presentation, and thank you for listening.